Yeah, good morning to all of you. In the previous lecture, we have discussed the concept of generalized momenta and cyclic coordinate for a given Lagrangian profile. But in previous example, we have a general profile of potential. Now, in this example or in this lecture, I will give you the exact profile of potential in order to analyze the concept of generalized momenta and cyclic coordinate and cyclic. So, we have this Lagrangian profile. The Lagrangian of a system which is 1 by 2 m r square r dot square r square theta dot square plus z dot square minus mgz. So corresponding to this Lagrangian, find out the generalized momenta and check the cyclic coordinate. Check the cyclic coordinate. Cyclic coordinate means we have to check in which direction are corresponding to which coordinate system our motion is conserved or our momenta is conserved. Our momenta is constant of motion. Our momenta is constant of motion. So let us see. So we have this Lagrangian which is L equal to 1 by 2 m r dot square theta dot square plus z dot square minus mgz. And we know that Lagrangian is simply t minus v. So this one is kinetic part and this one is potential part. So we have potential mgz. We have potential mgz. And this is the kinetic energy corresponding to which coordinate system? I have already explained in previous lecture that this is the simply r theta z. And r theta z is simply cylindrical coordinate system. So we will analyze the concept of generalized momenta first. Momenta, which is del L upon del QK dot is equal to PK. And what is K? What is our generalized coordinate in this system? This QK is simply generalized coordinate, which is r, theta and z. Our QK is r, theta and z because our Lagrangian is in r, theta and z. So we have three different generalized coordinate r, theta and z. So QK is, so corresponding we have three momenta. In this corresponding to this r we have PR. Corresponding to this theta coordinate we have generalized coordinate, we have p theta, and corresponding to this z we have pz, generalized momenta. So what is expression of generalized momenta? This is the general profile. So for r coordinate, what is our generalized momenta? Momenta is simply del L upon del QK dot, but in this case our QK is R, so del L upon del R dot, which is PR. So now differentiating this L partially with respect to R dot, so del L upon del R dot is simply del by del R dot, and what is L? L is 1 by 2 m r dot square theta dot square plus z dot square minus mgz. Now differentiating partially with respect to r dot, so this will give something, this will give 0, because if you are differentiating partially with respect to r dot, so theta dot, z dot and rest of the variable treated as a constant, and differentiation of constant is 0. So we have something, this will give 0, this will give 0, this will give 0. So del L upon del R dot is simply, let me take this 1 by 2 m outside. So what we have, del L upon del R dot, this will give 2r dot, this will give 0, this will z dot is also 0, and this one is also 0. So this 2 will cancel out, and what we have simply mr dot. So for r coordinate del L upon del R dot is simply PR, which is mr dot. This is the generalized momenta corresponding to R coordinate. This is generalized momenta corresponding to R coordinate. Similarly, we can find out the generalized momenta corresponding to theta coordinate. So for theta coordinate, del L upon del theta dot, because this is del L upon del QK dot, which is P theta. And what is our del L upon del theta dot is simply del by del theta. And what is your L? L is m r dot square r square theta dot square minus plus z dot square minus mg z. Now again differentiating partially with respect to theta dot. So theta dot, this will give 0, this will give something, and this will 0, this will 0. So let me take this 1 by 2m outside, and what we have, this is 0, this is r square, and if you will differentiate theta dot square with respect to theta dot, it will give 2r, 2 theta dot, plus 0 minus 0. So what we have, this 2 will cancel out, and we have simply mr square theta dot, which is del L upon del theta dot. So del L upon del theta dot is simply p theta, which is mr square. So this is generalized momenta corresponding to theta coordinate. Generalized momenta for corresponding to theta coordinate. So generalized momenta corresponding to theta coordinate. Next we have a z coordinate also. So corresponding to this z coordinate, we have generalized momenta, which is for z coordinate system. So what is your generalized momenta? Del L upon del z dot, because del L upon del QK dot. So del z dot is simply Pz, which is del by, and what is our del L upon del z? C. Now differentiating this L partially with respect to z dot. So this will give 0, del by del z dot 1 by 2 m r dot square theta dot square plus z dot square minus mg z. So this will give 0, this will give 0 if you are differentiating partially with respect to z dot. So r dot 0, theta dot 0, this will only gives, and this will give 0. So what we have simply 1 by 2m twice of z dots, which is simply mz dot. So del L upon